So that is an amazing video promoting Epic. I had to put it twice, but I hope you enjoyed it. And the fact that we're reaching to 800 members, I love it. And now it's exactly 3 o'clock. This means that it's time to start the today's online technology meeting on plastic sorting, recycling, and waste management. My name is Panagiotis Vergyris, and you can call me Panos. And for those that they do not know me yet, I'm the Photonics Technologies Program Manager in Epic. Before going further, and for the new faces in our audience, I would like to say a few things about who we are. We are Epic. We are the European Photonics Industry Consortium, and we are the world-leading industry association that promotes the sustainable development of organizations working in the field of photonics in Europe. And we now count almost 800 members, and we keep growing. The areas that Epic is active are many and variant. We organize technical workshops and roundtables. We serve and sustain a highly valuable network. We help you with market intelligence with the support of Tracy Vanik. We help you with raise capital, and we support also your HR activities with the biggest website to find a job in photonics. In this slide, you can see all the rest of the people behind this great effort of Epic. Let me now pass at our today's topic, which will be on plastic sorting, recycling, and waste management. The plan of this meeting, as all the meetings of Epic, is to create new business opportunities, to connect the people, and to introduce one to each other. And today we're going to listen what are the existing solutions in the market for plastic sorting, how they can be improved, and how they can serve the needs of big end users from the recycling and waste management field. I'm sure that we will be able to create important connections and new collaborations, and I hope as well. Here you can see an overview of all the upcoming technology meetings for the next months. And here I highlight a few of them that might be of interest for the audience today. In 2 days, we have a physical meeting in Leipzig in Stuttgart on beam sending for industrial applications. We're going to have an industrial quantum photonics technology summit in University of Glasgow in September, physical as well. We have some online meetings on aesthetics and cosmetics and mobility of the future. Later in November, we have optical fiber sensing for monitoring and Earth observation, which is also very important here. Topic is hyperspectral imaging. We have a meeting on medical devices, and finally, the classical every year meeting that we're doing on food and beverages. And at this point, I would like to thank the sponsors of this meeting, Avantes, that offers enabling spectroscopy solutions for the environmental industry, Art Photonics, that develop and produce specialty fibers, fiber probes, laser cables, and bundles for very broad spectral range from UV to mid-infrared, and Vortex optical coatings that design and manufactures optical coatings and filters for scientific instruments and sensing. Vortex actually is here today and will also be one of those speakers later. So we'll have the chance to learn more about them later on. If any of you would like to get introduced to any of the other participants of the meeting, they can always contact me afterwards in my mail, panagiotis.vergyris@epic-asoc.com. The ones in the room are requested to actively participate in the meeting today, ask the technology-related questions that we have. This is an open discussion. We can, of course, put in the chat and we'll bring it in the room to share with all the participants. So you just raise your hand with the sign on the Zoom choices that you have. Before I continue, I would like to remind you that those meetings are recorded and live streamed on YouTube. So remember that those that are following YouTube can also ask questions, and we'll try to bring them in the room and address them. We're going to do our best. And now let's see who is actually in the room today. This slide here represents all the people that sign up for this meeting. And basically, if you look at yourself, you can see that it represents really the full chain of today's topic. We started with some end users like Sesotec, PICVISA, Steiner, and others. We have many from the side of sensing, like cameras and hyperspectral, X-ray and SWIR solutions, and also from the sensor side. We have representatives from optics and optical systems, and from the metrology side as well. And of course, the list does not end here. And now let's pass to our speakers for today. Our first speaker for today will be Tobias Eder, Manager Application Engineering and Technology Markets Lands in Sesotec, I'm sorry. Charle Musoll, Computer Vision and R&D Engineering PICVISA. Wouter, Program Manager in imec. Gerhard Stanzel, Product Specialist at SPECIM and Konica Minolta. Reilly, Managing Director of Vortex Optical Coatings, and Isaure, the Kernier Application Scientist at First Light Imaging. Now I would like to stop sharing. Welcome everybody, and ask Tobias to share his screen and his slides, and the floor is yours, Tobias.
Thank you very much for the opportunity to speak here. Give me a second. Can you see my screen?
We can. Crystal clear.
Okay, I'll talk on the behalf of Sesotec and we'll show you our first slide a little bit about our company. We were founded in 1976. We have about 540 employees right now over the whole company worldwide. Our R&D growth is at 10%, and Sesotec is divided in 3 business units. We have the sorting recycling unit, which I'm belonging to. We have a product inspection part for food and also for plast. And we have about 2,300 recycling systems installed worldwide right now. Totally, with the other product units, it will be 83,000. Below there in the picture, you can see some small examples for some turnkey solutions. Our smallest belt sorter, together with a sieve and a conveyor belt and an infeed hopper, and 2 flake sorters for flake sorting. Oh, sorry. Then we come already to our products. We offer different products. For example, our Vergyris Plus system. It's mainly made for bottle recycling, HDP and PET bottles, and can sort up to 8 tons per hour throughput at a 2.8 meter width span. Then we have our Vergyris V. It's mainly used for electronic waste, car scrap, ASR, cable sorting, and also metal sorting. Then we have our Flake Purifier Plus. It's used for sorting PET flakes from 2 millimeter upwards with 3 tons per hour sorting capacity per meter working width. Our smallest belt sorter, the Vergyris Compact, it's available up to 1.5 meter working width and can sort 3.8 tons. And then we have our newest addition, the Flake Scan. It's only used for quality analysis to be sure what is your input material, what is your output material. And it analyzes, helps the customers to get rid of problems in the process and so on. All machines are equipped with our sensors that will be shown on this side. We have our C sensor, it's a color and shape sensor. Our M, respective M plus sensor, which is an all metal sensor, and also can be used as the plus version for metal detection and entity identification. And we have a hyperspectral imaging sensor. Here you can see in the picture the operating principle of our sorter. We have a conveyor belt where the material is fed to the sensors. We have an all metal sensor bar below the belt, which detects all foreign metals. Then we have our near infrared lighting and sensor for the near infrared detection. And we have different lighting options for our color detection. And then we have 2 air ejection systems. One can blow from the upper side, one from the lower side, and all contaminants will be blown either to the 3rd chute in this case, or to the 1st chute, for example, cans and so on, alloy cans, and false polymers will be blown in the 3rd chute then and divided into 3 fractions in 1 sorting step. For the M plus sensor, we can also distinguish between alloy and stainless steel, for example. But the M plus sensor will not be topic of the other slides. It's not mainly in your business. So we focus on the color detection. Therefore, we use actual CCD line scan camera with the resolution from 0.375 millimeters and about 17 million teachable colors. As you have seen in the slide before, we can use it with different lighting options. We have a transmissive light, a reflective light, and also a basic light where we use the NRR light source for the color detection. The applications for it are mainly the sorting of the color decontaminations, sorting by shape. For example, we have a shape detection for colors, for round objects, and so on. You can adjust it very sensitive to each fraction you want to know. And you can also sample transparent from non-transparent material like in PET flakes. We're also working at an AI solution for this one. The first results were already very promising, but therefore I come back later. And for the end sensor, we use our own developed NR camera, where we only buy the sensor. The rest is really on our own. And that is mainly used for flame retardant detection. We can distinguish if it's a PET mono bottle, PET tray, or so on, so that we can also sort these. We can differentiate between LDPE and HDPE, HDPE bottle and foamed HDPE. So there are really slight variances in the spectral image, and we can still detect them. The plastic library, that's also good for our customers, can be adapted to their needs. So if they can show up with a problem they have, they send the material to us. We do a special plastic library for their sorter, install it, and then they also can sort it to solve their problem. Well, what are the challenges right now in recycling? Oh, sorry, wrong button. What technology is needed right now? What we really were looking for would be a reliable technology that can detect black polymers with a detection accuracy like the NIR sensor has. So right now we only have some possibilities with MIR and so on, but it's not already the same level like NIR is. Also in combination with some tetrahertz cameras and so on. There have been many projects also from the Fraunhofer Institute, I think, but there are no real results that are possible for an industrial scale at the purities our customers need. Our next thing would be LED with 1300 to 1900 nanometers, where we can really do the NIR sorting to get rid of those halogen bulbs and so on, to lower the power consumption a little bit. And we really need a powerful LED lighting to allow also the detection of darker NIR or darker polymers, because NIR still has the problem that carbon black can't be detected right now. And one third thing we would need, especially for the AI theme, regarding the artificial intelligence, will be the computing power. There I read an interesting article of Carlos Lee, it's also from EPIC. That would really be helpful for future applications to get those huge amount of data calculated and to shorten the time till between detection and the time the product has to be blown out. What we could offer to the members of EPIC is the opportunity to test the products you have or the sensors in an industrial environment, either in our test center here. We're just about building a new test line for approximately 1 million euros, or also at a customer site. You will get detailed feedback of our findings, what should need to improve, what was good, and so on, with test results and so on. We can also offer you a cooperation in research projects. We already did like Polymark project from funded by the EU and so on. And we also can offer you, under our experience of 40 years in the recycling business and the detection of contaminations, material sorting, and the analysis. Then we already are at my last slide, the future of recycling. I've been to the PETCOR conference in Brussels last week, and what will definitely come is the closed loop recycling for bottles. So Coca-Cola said they want to be establish a 100% rPET bottle by 2025, and many others, the Schwarz Group, where Lidl belongs to, already have their own recycling systems with their own deposit return system, and they all want to produce bottles again from their sold bottles. They collect it, regrind them, get the polymer back to make new bottles. The growth rate for waste separation is estimated to be 8.2% annual till 2030. So it's a big growing market. And fueled by the high targets from the European Parliament for the use of recyclates. So there must be a certain amount of it in new products also. Then what technology for the future will definitely be the artificial intelligence. I know everyone's talking about it right now, but for the cycling, for the waste stream, it really will be a real big benefit, also for material detection. Waste is becoming an increasingly important new raw material. Also, if you take a look at the oil price, so the virgin PET is getting more and more expensive. And therefore, the recycled PET, for example, can be one solution. And the future, we will also use some new sensors like LIPS, XRF, XRT, which we not use currently in our recycling branch, but we also use it in our food detection equipment already. Then laser, MIR, and tetrahed cameras, and so on. So we never know if some new sensor could be equipped in our sorting recycling equipment. So that's for my side. Thank you very much for listening to this short presentation, and please ask your questions.
Thanks a lot, Tobias. Thank you a lot. So
you're welcome.
That was very interesting. Actually, you already came here with very triggering slides, especially when you spoke about the needs that recycling field now has from the photonics market. So I'm expecting somebody from here to raise a hand and answer to Tobias if you have any solution at the moment out there. But in the meantime, I will go to some questions that we already have in our chat. One comes from Demcon Focal. Sorry, it is Albert Borman. Albert, if you want, you can. Yeah, perfect. You can ask the question yourself.
Yeah, thank you. It's a nice presentation. I'm really interested in this this topic. So thank you for the clear picture and also what you guys already can do. What I also understand, especially from some people here in the Netherlands, that they are looking for food grade plastic. So and they would like to detect that. And I wonder if you already looked into that part.
That will be some projects like Holy Grail 1 was already, or Holy Grail 2, where we also take part. And it's more about digital watermarks right now. So there will be a small QR code invisible for the eye, printed or embossed within the polymer the whole way around the bottle and detected by a camera systems and calculated, and then it could be detected. Yes.
Yeah. Okay. That so the whole grill that I didn't know about that project, but
it's Holy Grail 2.0. It's a big initiative driven by AIM.
Okay.
So,
thank you.
You're welcome.
Thanks a lot, Albert. There is one more question that comes actually from Alessandro Rosetta from Clean Labs. That they're working in another solution for spectroscopy. Alessandro?
Thank you. Hi, Tobias. My question is, have you ever looked already into fluorescence-based solution? I'm talking about fluorescence lifetime. We now are developing, we develop instrumentation for measuring the lifetime either in spectroscopy or imaging, and we are working on a microplastics detection project based on the lifetime of the microplastics. So based on the lifetime of the microplastics, we can distinguish them. So have you ever considering maybe using this approach, so shining a beam of light?
We tried it, but only due to the Polymark project. It was about 5 years ago, I think. It was an EU-funded project, and there they had an ultraviolet marker mixed into the PET bottles. And with the ultraviolet light source and a special camera unit, we tried to detect it. But it's always hard if you want to mix some markers into food grade stuff to get the food grade approval and so on. But for the rest, XRF would be then our solution for the metal part of the recycling. But for the polymers, we have not looked to it right now.
The solution that we are testing, it's something that doesn't have to have, let's say, a specific marker or a dye. It's going to be labels free. So the labels free, for most of the cases, it works. But there are some, let's say, borderline cases in which it may not work. But still, this label-free approach would solve all the issues of labeling, or everything that goes into the instrument.
Yeah, labels are also a big issue in sorting. Yeah.
No, I know. But if you, let's say, try and use a label-free approach, for example, we are using visible light at 440 nanometers. So this will excite fluorescence and will excite, let's say, a lifetime response that is variable depending if I am looking at PET, PVC, nylon, and so on. So maybe using, instead of a camera approach, a single pointer approach with visible light instead of UV or near infrared. That's what I am, let's say, trying to pitch.
Okay, no, we did not try that, but if you have more information on that, I'm happy.
I do. I'll drop you a couple of lines afterwards, and maybe we can get in touch and have a
discussion. Thank you very much.
Thank you.
Thank you, Alessandro. Thanks a lot. I will continue with the questions, but before going to that, I see that we have a lot of attendees. You get an invitation to become panelists. Please accept it so you can have your own questions and participate in the meeting. Again, please accept to become panelists. I'm speaking to the attendees. The next question comes from Zeiss, from Fanny Seus. Fanny, you can ask the question yourself, please.
Yeah, so actually it was going into the same direction as the first one, looking for the initiatives around distinguishing food grade materials. So you already talked about Holy Grail. I don't know whether you can say anything about Next Loop or other projects who do about tracers. So it's not digital watermarks, but like chemical tracers and fluorescent light. Whether you know anything about that. What do you think about this? And what do your customers think about that?
For the customers, I think it's not the main issue to sort it, because you only need some other kind of technology in your sorter. But I think for the end users who will use the food grade stuff again, it will be a problem to mix some chemicals into their food packaging. And also to get the approval for that, because you can't never ensure that you have a 100% clean fraction. And also the tracers will go to other kind of polymers then. And then if you mix it up somehow it could be a problem in the future.
Okay, but okay, they say they have like a process where they can decontaminize the polymer. And from the detection side,
from the detection side, I think it shouldn't be a problem. If you have any fluorescent markers or so on, it's only another camera system, another lightning you lead as a special wavelength, and it should work.
Okay. Thank you.
Thanks a lot, Fanny. Thanks a lot, Tobias. One more question comes from NKT Photonics. Deepak Nair.
Hello, thank you. Myself, Deepak Nair from NKT Photonics. I'm a product specialist for the supercontinuum lasers. So obviously my question is that I can see that you're interested in an LED source covering 1300 to 1900 nanometers. So why not a supercontinuum light source? Because we offer supercontinuum light sources that have the full short-wave infrared capabilities, all the way from 1 micron to 2500 nanometers. So will that be interesting?
Yeah, for sure. I only talked to our development department and they gave me a list of what they need.
Okay.
And then I picked out the main targets for me.
All right, because I can see that the camera that you use has a line scan resolution of less than a millimeter. It's close to 400 microns. So that would require a really, fine line from the light source, right? Which would be really hard to accomplish with an LED. But on the other hand, if it's a super
the
resolution
resolution was for the color sensor.
Okay.
So the NR sensor is a little bit bigger.
It's probably wider, yeah. But again, this is a real laser, right? With a diffraction limited light. So going down to the micron levels.
You can also send me some info about that, and I'll hand it on
definitely,
to our development.
yes. Okay, I'll get back in touch with you. Thank you.
Yeah, thank you very much.
Cheers.
Perfect. And that's why we do those meetings, in order to connect people. You can come back to me and I'll connect you to Tobias if you cannot find his email. And I will go to the next question that comes from Peter Totrup, NLIR. Peter?
Yeah, hello, I'm Peter. We have just recently worked with some black plastic sorting with a university in US, and I already sent you the link to the paper. So we have done, they have just done some deep learning stuff, and they have like a very nice computer matrix with almost 100% in all plastic types. So
Okay.
and kilohertz sample rate. So
Okay.
so we visited before, but I mean, I just gave you the latest status on what we are doing in the plastic sorting.
Yeah, thank you very much.
Thank you, Tobias.
Great. One of the biggest problems in recycling, I would say.
Okay, that's great, and we're happy, yeah. And I think it comes to another question. Maybe we have also a solution from Ross Stanley from 4K MEMS. He wants some more details about the LEDs you are looking into. Ross?
Yeah, hi. Thanks for the talk. Yeah, I'm really interested in what kind of power you want from these LEDs, because and how much bandwidth. Do you need the whole 600 nanometers?
Yeah, almost, because we really have a hyperspectral image, and for some sorting applications, we really need to differentiate very strict or very detailed between the spectral images.
And tungsten sources are just not intense enough. Is that it, or?
Yes, they are, but our development would rather stick to some LED light source and so on. So.
Due to lifetime or power?
Both, I think.
Okay.
Mainly lifetime, I think.
Okay. Because we're developing very, very small tungsten sources, which can be made into arrays, so they could be very easy for making such line imaging.
Yeah, can you also send me some information about that, and I'll hand it on to our lightning specialist.
Okay.
Sure.
With pleasure.
Thank you.
Perfect. Thanks, Ross. As you said, Tobias, I think you have a lot of job after this one.
Yeah, I have a lot of work.
Perfect. We're happy. Thanks again for the presentation. We don't have another question, so I would like to go to the next speaker for today. The next speaker for today is Carles Musoll from PICVISA. Carles, if you can share your screen.
Yeah.
Perfect.
Thank you very much.
And, perfect. We can see it.
Can you see? Okay. So thank you very much. Good afternoon, everyone. I will briefly introduce myself. My name is Carles Musoll, and I am computer vision engineer at PICVISA. I am in charge of developing applications that involve either hyperspectral imaging or deep learning algorithms to solve new challenges in sorting. Let me introduce PICVISA. PICVISA is a technology company that offers solutions on machine vision. Most of the solutions can already incorporate artificial intelligence, focus on object detection, and instant segmentation. PICVISA plays a key role in the circular economy, concurrently in the collection stage. PICVISA's main objective is offer waste managers as well as recyclers solutions that provide optimal materials for recycling while reducing the loss of recoverable ones. For that purpose, we work in what we call intelligent sorting. Intelligent sorting includes both the use of deep learning algorithms and the correct combinations of systems to take advantage of each one. Let me give you an example. For a proper polyethylene recycling, the input material must be free of problematic packaging, such as silicone tubes. With the current near-infrared classification, this is not possible, and we leverage deep learning to detect the object in order to reject it. In the following slide, I am going to show you different solutions that we provide. EcoGlass is designed for glass sorting. It basically uses RGB image to sort glass of different colors, as well as to clean a glass flow from impurities. EcoPack is the most versatile machines. It can treat any flow on a conveyor belt. it can build several systems which are combined with each other depending on the application. The systems are near infrared, visible near infrared, RGB cameras, or inductive system. And then based on the EcoPack, the EcoPeak also can treat any flow on the conveyor belt. The difference is the rejection system, which is done by a Delta robot, unlike the EcoPack that is done by means of an airflow. The main goal is to replace manual labor in quality control stage in waste management facilities, but it could have other applications. And then EcoFlow is basically an EcoPeak without a rejection or extraction system, since their purpose is just to monitorize any flow, giving valuable data for decision making. And finally, there is EcoSort, which is an adaptation of EcoPack with multiple outputs. It has been recently used for the classification of different types of textile garments, depending on their color and composition. Excuse me. And once the different solutions has been presented, and although I have already advanced some of the applications, all of them are shown on this slide. There are 4 main applications: municipal and industrial waste. These include basically all plastic and glass sorting applications, textile, applications that I have talked about in the previous slide, and construction and demolition, and coffee capsules. This last application is very recent, and its goal is to recover coffee capsules, among other plastics such as bottle tabs and yogurts, from a flow that right now nothing is recovered. It is worth to mention that PICVISA was granted by European funds and other financial sources for providing new improvements in circular economy. And finally, I would like to briefly outline some of the challenges that we are currently facing or we will face in the near future. From the hardware perspective, we are working on remove GPU dependence where possible. On sensor side, we are testing medium infrared camera to tackle black plastic sorting, although there are more and more initiatives to remove carbon black as pigment. Deep learning has helped us to take a huge leap in our sorting applications. That is why we are always on the lookout for new developments in this field. Currently, we are working on a self-supervised project in order to reduce the cost associated with object annotation. In the lighting section, I would like to mention that we will assess the use of LED lights in the infrared range with the aim of making optical sortings more energy efficient. And finally, we are now integrating 3D technology into EcoPeak in order to optimize the picking process. But we believe that 3D can bring us many other advantages in the future applications. Thank you very much for your attention, and I will be happy to answer any question you may have.
Thanks a lot, Carlos. Thanks a lot. Perfect. Now we can see also your face, just observe the screen. It's great, actually. We just see the last slide having some challenges being repeated to the community of photonics, and it's kind of the same. So you already heard some answers from NKT Photonics for superconducting lasers and other approaches for other photonic solutions that we can offer. But still, if there is more questions from Carlos, please raise your hand or ask it, and we'll bring you in the room. Before going, because there is already one question from Demko Fogel, from Albert Bormann. Before going to him, I just want to ask something that we didn't ask before, neither to Tobias. What do you think is the biggest challenge now for plastic sorting when it comes to photonics? Where you really miss something? It's a black plastic sorting, or it's a LED, for example?
Maybe a black plastic. sorting.
Okay, and your feeling is that where we should direct ourselves in order to have a solution over there? Will be deep learning able to help you in the future?
We not yet tried the mid-infrared camera that arrived 2 weeks ago, and I don't have results to know if the camera could be suitable to black plus sorting. And I think deep learning here, I think it couldn't help to black plus sorting.
I can imagine it's one that can really measure physical parameters here.
Yeah,
no?
yeah.
To...
We need the information of material, and deep learning. Deep learning help us a lot for example, to sort the bottle from trays. The other example that I said before, for example, cleaning an HDP flow from silicone tubes, because we cannot detect the silicone inside the packaging. What else? And there are other applications, but right now I don't remember.
That's fine. That's fine.
But it's deep learning helps us a lot when near infrared can we cannot when near infrared can go, for example, to detect silicone tubes. Maybe we can use the a wavelength image of the multiple image that we have in the hyperspectral cube to detect the silicone tubes. This is another project, but with only the response of the spectral response, we cannot detect the silicone tubes or the.
I see. I see. Thanks a lot. Let's go to the next question, though. It's from Albert Borman. Albert.
Yeah, thank you. Yeah, Carlos, I have one question, because what I understand is that you use machine vision in your application, also spectroscopy, in order to do the proper sorting. But you have to train your machine vision algorithm. So how do you do the training? Because there's a lot of packages around, and new packages are coming by. So how do you do the training of machine vision?
We train our models in our server, and then when we will test, and then we will release the model.
And that's for example, for each bottle you have to train your setup.
Maybe we have I know maybe we have more than 2,000 image, and annotate every bottle of the image to then put it in the algorithm to train the model. It's the way people train the deep learning models, the supervised deep learning models.
Yeah, we look into that part as well, because but the thing is, of course, annotation of this data is a hell of a job. Yeah. And we are looking into the direction of why not using what we call synthetic data. We generate our own data, our own packages, and make all kinds of forms, and then use that as in our machine vision.
I didn't put in the challenge the synthetic data, because I am quite skeptic that synthetic data could help in that. But we keep in mind to try the synthetic data to train our models.
Okay. Well, yeah.
But personally, I am quite.
Oh yeah, well, I'm curious why. I'm curious why you are skeptic. But yeah, maybe should discuss that offline. But it's interesting to see. yeah, because this annotation of this data and train your machine vision with all different packages is a hell of a job. So you need to do something there. I think.
Okay, thanks a lot. I'm sorry for interrupting, but we have more questions coming out there. So the next question comes from Wolfgang Marzinger. Wolfgang, you want to ask the question yourself, please? If not, I will bring it in the room. It's which spectral region do you mean with wave infrared? Do you mean the near infrared region?
No. It's I don't remember exactly the range, but it's 3 micrometers up to 5.
Okay, so 2.5 to 3. Okay, thank you. Next question comes from Gerhard Stanzel from SPECIM.
Yeah, just a question. So have you thought about using publicly available data? So because this is a problem, huge data sets for AI training, but there are already projects, initiatives where they share like 20,000 or even more pictures of real waste. Yeah, just if you're not aware. So I think they're not so easy, not so hard to find, but I know there are some out there.
No, we use our own image. We don't use.
Okay.
We don't use public images. We use the images that our machine recording the waste that pass through the machine, and then we annotate the image, and no, it's not a public image. It's not
okay, then it is a lot of work. I agree.
Yeah. No.
Thank you. Thanks a lot, Gerhard, for the question, and thanks, Carlos, for answering. One more question comes from imec, Wouter Charle.
Hello. It's more a general question for plastic sorting that I had, since now already twice in two presentations it came up that one of the challenges is black plastic. But I was wondering, some challenges that we also see coming by from time to time is on transparent plastic. So then do I understand that this is a problem that you see as a very solvable problem, or that's also in the same, or still also a challenge on transparent plastics and also contamination of plastics? Like I was wondering what other challenges are there today that you're dealing with or struggling to solve?
But transparent plastics could be a problem. It depends on the thickness of the plastic. And another problems that the issues that we have is, for example, from film plastics, when there are a lot of layers in film plastics, it's very difficult to distinguish all the layers in films. Even for example in PET trays, there are monolayer trays, but there are also multi-layer trays, and sometimes we can distinguish maybe the first layer, but in transparent layers it's very difficult to distinguish all the layers, because sometimes there are also adhesives between the layers that sometimes the customers ask for if we can detect the type of adhesive between, for example, PET and PE layers, and we cannot distinguish the adhesive.
Okay.
Maybe it's in transparent plastics, or even in opaque plastics, the multi-layer plastics is a very large issue.
Okay, thanks a lot, Carlos. And Tobias, you want to answer the same question because it was also addressed to you. You can say you have a comment or something.
Yes, for PT trace, we can distinguish already between monolayer and multilayer. That is possible.
Yeah.
And the rest is really if the plastic is getting too thin, like a film or something, then you get a too bad signal for the NIR sensor, and there it's really hard to solve it. But the main issue is the mechanical thing about the films, that they don't flow like solid material on the conveyor belt or on the slider or so on. And for the PET bottles, there are also some juice bottles, orange juice, which are equipped with multi-layers, a PA, a nylon layer inside. That's already partly possible with AI. So you teach really the problem bottles to your learn set, and then you can get rid of these specific bottles with the use of artificial intelligence.
Perfect. Thanks a lot. Thanks a lot. There is one more question, but we don't have a lot of time, so I want to make it myself. It comes from Dominique Bonisser from Thematis. The question has to do with the market demand. What is the required production capacity? How many tons per hour to be sorted out? So if you can give us just a number for her to answer, that would be great. Is it easy or not?
How many tons per hour to be sorted out?
To be sorted out. The market demand.
In plastic sorting, if I remember well, it's about 1 ton. I don't remember exactly, but I think it's 1 ton every half a meter. So I think it's 4 tons per 4 tons. It depends on the width of the machine, but for example, for a 2 meters wide machine, it's 4 tons.
Thanks a lot.
4 tons.
Yeah, for a big recycling plant, it also depends on the extruder. How many material needs to be fed that it's continuously running. So it's also dependent of that. And for our sorters, for the bottle stage, we have some sorters or some plants which run 8 tons per hour, and for the flake stage, then 6 or 7 tons per hour.
Perfect. Thanks a lot, Tobias. Thank you. So I would like to go to the next speaker. Thanks a lot, both Tobias and Charles, for presenting the end user side today. And the next speaker will be from imec. The last question that we have. Wouter Charles. Wouter, you're still muted. You're still muted.
Thanks. With sharing the screen, I couldn't find the button anymore to unmute myself. So thanks for your help. So hi everyone, I'm Wouter from imec, program manager from the electrospectral imaging technology. Happy to connect today with you at the application for plastic sorting and recycling. Today, I want to introduce our activity and zoom in a bit on our development in short-wave infrared sensing technology, spectral imaging. So our core capability at imec, our core innovation, is that we develop an on-chip filtering technology that enables miniaturization and scaling up cost-effectively spectral imaging technology, but also true spectral snapshot video rate imaging. And with that we hope to innovate and commoditize spectral imaging. Our strength, I would say, is to connect from technology all the way to the application and see with application companies how spectral imaging, how this new technology can help solve their problem. Also which system aspects need to be considered, like also illumination and lens systems, and then how our technology can help to bring a cost-effective solution to their application space. And we go all the way from we have developed an evaluation system offering, and we can go all the way to customization of filters, but that's not always required. So we try to produce sensing solutions that serve a broad application range, by considering application requirements and then providing an off-the-shelf solution. For more information, please have a look on our website, imec-hyperspectral.com, and you can always contact us on hsi.sales@imec.be for more questions. So specifically today, I want to highlight the snapshot spectral camera that we have made. This is a camera with 9 spectral bands, and that we have positioned specifically on application inputs. So what we have done, since we put 9 spectral bands on to cover the short infrared range from 1.1 to 1.7 micron, we cannot make it hyperspectral, so we cannot cover continuously the whole spectrum, but rather what we have done is looking at where are the critical absorption peaks for different applications, and then position the 9 spectral channels accordingly. And so with that, we managed to cover a wide range of applications, and one of them is, of course, sorting. So what we have done for sorting, both for textile and plastic, is for plastics putting the channels in the beginning of the spectral range, so that we can be sensitive to the different polymer chain length absorption peaks, and then for textiles, making sure that we can also have the right absorptions for the different types of, like wool or cotton, or different types of fabrics. So how does it work? But I guess that many people already know. So we capture a spectrum. A spectrum corresponds to the material properties of what we are looking at. And this is combined with a spectral video system directly with a full field of view image. So we also have the spatial information combined with that. And when input in then a model, we can classify based on both spectral and spatial information to detect this is that kind of material, and make a decision. So this information comes from a feasibility study that we have conducted, where we are, for instance, here having different types of plastics, but also paper and cardboard combined in one classifier, and we managed to pull them apart. Giving a bit more insight, so with plastics, for instance, these are the kind of plastics that we have tested. So here we can see different absorption peaks in the beginning of the wavelength range, and the change in spectral signature will then be used by the algorithm to just, based in this case on spectral shape, to decide this is this type of plastic. On fabrics, the same can be done, and we can also see that with this information, just making use of the spectral information, we can really have a very robust estimate of the type of fabric that we are looking at. So then we have extended that feasibility study, and in the end we have managed to get a very robust classifier for a wide range of applications, and this is then just using the 9 spectral channels of the spectral camera, giving us outputs the different classification decisions. So in the end, so this is for the mixed data set, and also on fabrics we have trained a classifier with, if I remember correctly, up to 18 different materials, and the classifier is capable of having 95% accuracy in detecting the or in making a decision. Now, why is this important, or what is then the promise of or what do I think is the promise of snapshot video rate imaging with this technology, is that it enables capturing an image in a single shot and immediately taking decisions. So that removes a lot of constraints of a traditional line scanning system, where you need to scan lines to form an image. If combined in, for instance, if you have this on a system where you have a lot more chaos, or if you don't have the the ability to nicely spread your goods on a conveyor belt, then you can take a snapshot and take a decision directly of the bulk that you're processing, interact with the bulk like with a picker or an ejection system, and immediately the next image comes and you know what was underneath. You can take another decision. Or you could also mount this on robots that will act in this non-well controlled environment. So in that sense, conveyor belt systems can be either more packed or are not needed anymore, because you could also do this on the bulk coming in, either dumped by a truck or stored in bins. So now I also have a small demo I prepared. I was first going to give the demo from our demo studio, but since there's limited time, I did not want to go to the full risk. So this is our demo studio. This is the camera that we used in this setup. And this is the small video I have prepared. Just to show you how the data would look like with a spectral snapshot imager. So this is live data where I have now gone through several bands. And now what we will do is interact with the data to show the spectral signature underneath, and then use that to build a classifier. So in this software, we are using a spectral angle mapper, which is a correlation-based classifier, but already just using the correlation between the different spectral signatures, you can make a lot of, you can see that there's really a lot of information or a good classification decision coming out already. And this example was taken from, was a feasibility developed in the Vision to Reuse project, where one of the problems of the industry is to detect when they store reusable plastics, if there is still liquids on the plastic. And so here in this demo, we can see that the camera can correctly classify not only the different types of plastics. So here we could see which type of plastic it is. I'm not sure in this case what it was exactly, but we can also see what is the water, which plastics have water on them. And so as such, you can then the factories in this case could then see which plastics have water and which can be stored, and if there's water on it, they can maybe do another drying step or put it on a different type of line so that they would not suffer from fungus or from natural processes forming during the storage of the plastics, so that these plastics can effectively be reused. So this is to give an example. So here this is even showing where there is thick patches of water or thin, where there are other types of materials mixed. But that's the kind of data coming out of these cameras. And yeah, given that it's snapshot video and completely directly imaging a complete field of view, I hope this can inspire and bring to new ideas, and yeah, I'm open, or I look forward to discuss some ideas and also to see which questions you might have. So in a nutshell, there's a lot of recycling applications in short-wave infrared range. Putting the 9 channels at right positions enable these. Textiles, plastic, paper, and other materials can be classified with high accuracy. Snapshot imaging with our technology gives compact behavior, low cost, scalable, high speed, and easy to integrate as it behaves like a regular industrial camera. And then we can drop a lot of the constraints on our environment, because we don't need necessarily to have the linear motion, and we don't need to have everything nicely spread on a conveyor belt. We can deal with a lot more chaos because of the video rates and immediate capturing behavior. So this is what we did. This is what I wanted to bring today, and I hope to inspire. So thanks for attending.
Thanks a lot, Wouter. Thanks a lot. Really nice presentation, and I really enjoyed the demo video that you had there.
Thank you.
I have a question. I mean, please ask questions to Wouter, but I have a question before. My question is simple. Can we think about having speed issues or acquisition speed issues when we're thinking of installing those hyperspectral cameras into sorting belts?
So the frame rate of the camera can go up to 120 FPS in this implementation. And of course, the nature is very different from line scan, where you need to have very high rates because you need to acquire the lines. Here we are capturing, it's really point and shoot. So in one capture that takes, depending on the illumination condition, typically 1 to 5 milliseconds. You have in one capture, you have the spatial and spectral information. And then at a high frame rate of up to 120 FPS, exposure time allowing, of course, then you have a very fast refresh rate. So the situations that I have in mind where this technology can really make a difference is where you have a dynamic interaction of your robot with the bulk stream. So the robot is picking, and instantaneously you have a new picture of what was underneath. So by the time the robot is back to pick the next thing, you already know what was underneath, so you can make the next decision. Or if you have a faster ejector system with compressed air, you eject, you snap, and you can immediately eject again. So you don't need to have like a round-robin scanning system. You could just install this on a bin and have a robot empty the bin, and when it's done, you exchange the bin and you have it happen again. So in terms of factory footprint, this could really have a big impact, I think. Or in also the equipment installation. Like I saw PICVISA, you had a Delta robot, but then you still have a scanning system. So then I was thinking, if you have a snapshot imaging system that co-ops with the Delta robot, you could maybe also speed up or make it more compact in solution.
Perfect, thank you. Carlos, if you want to answer the question of, the comment of Wouter, you can. In the meantime, I will go to the next question, which comes from Wolfgang. Hello, Wolfgang. Marzinger, it's a little bit difficult name. I hope I pronounce it well. The floor is yours. You can ask the question yourself.
No problem. Can you hear me now? Yes. Okay.
Yes, we cannot. We can not very well, but we can.
Okay. So my question is simply, do you plan also to introduce cameras with different spectral regions in the market? Because now you have introduced a camera which is exactly defined at this near infrared range you are showing. Do you also plan to extend this range, or to develop some slightly different products?
So today we have put this short infrared 9-channel camera on the market to show what we can do. So we can we already have the snapshot on CMOS, so spanning the system. We have systems in vis, red, and IR near infrared range. We don't have any variation on the SWIR imager on our roadmap today, but we can easily adapt to requirements of our customers. And then we are looking, but that's more today through bilateral and funded projects, to extend the range to higher wavelengths. So then I'm thinking full shortwave infrared up to 2.5 micron, and maybe also EMEA on a longer term. In principle, so we are a filter technology company, or a filter technology group, I should say, within imec. So in principle, there's no reason why we would not be able to do that. Of course, if we go to higher wavelength ranges, the cost becomes a different, the detector cost comes to different aspects.
Okay, thanks a lot. Thanks a lot, Wouter. Do you have any other question for Wouter? It seems that not, but if you have any other question later, we can come back. Thanks again for the presentation and for the really nice product, and it's very inspiring. I would like now to go to the next speaker. The next speaker for today is Gerhard Hansel from SPECIM. Gerhard. Thanks again, Wouter.
My pleasure.
Hi, can you see my screen? Is it working?
You can still... No, not yet. You have to share. You haven't shared yet.
Thought I just selected the right. I have to click the the other button too. Not just select the screen, but also give it free. Okay, so thanks a lot, everybody, and also for the possibility to speak today. My name is Gerhard Stanzel. I'm a product specialist for SPECIM at Konica Minolta Sensing Europe. SPECIM slogan is spectral imaging made easy. Today, we want to do it or show it in recycling. And I'll just show a few examples of what we do and how it can help in recycling. So as you probably know, SPECIM is a hyperspectral company, hyperspectral manufacturer of cameras, started in the 90s already, mid of the 90s. So soon you will have 30 years. And spectroscopy is nothing new. Spectral imaging is a bit newer, but based on the same principles. And of course, it can be used in a lot of areas like agriculture, food, waste sorting, and so on. But for example, also food could be a topic in the recycling environment, how to recycle food in the future in the right way. Also, probably pharmaceutical products, who knows? So we all know waste is a global problem. So it's 2 billion tons of solid waste in 2016, and based on data from United Nations, from Statista, whatever, so the world produces 300 million tons just of plastic waste every year. And to give it to a number, to a relation, that's the weight of the entire human population every year, and this is quite a lot. And we know, especially plastics are a super big problem. The thing is, the waste is not going to get down lower within the next years and decades. It will even get more. So the problem is what to do with that, except of dumping it or burning it. So the next step could be to think about what is the waste made of. So municipal waste is made of different things. Of course, we eat a lot of things. It's rests of food. We have green stuff and so on. This is actually quite a lot. And just getting out this one, or this is even sorted or collected separately, is already a big step, because all food and green stuff can be composted, recycled in a very nice way that nature already prepared for us. And then it comes to man-made products like paper and cardboard, especially plastics is quite a big thing. It works quite fine already for glass and metal, as these products are relatively good to recycle. Others are less often contained, like rubber, leather, also wood in household weight is not that much, but there can be anything else. And the other materials are already also quite a lot. Hyperspectral imaging can help in almost all of these areas. There might be some question marks on how can it help for metal, because there are no absorbance bands and so on, but we can also discuss this later, especially for plastics, paper, cardboard, finding out food rests, food waste in the material stream. It's already possible to do that. Also textiles, we've already seen that today, and not the typical municipal waste, but also a very big portion of the waste is construction and demolition waste. So what to do? So we recycle. What SPECIM has made is the SPECIM 1. So with the idea to make it easy to use systems like that, also for companies that are getting new into the area. I've recently seen quite a lot of robotic companies, robot picking companies. They typically combine different sensor systems. But one of the data that is clearly very, very helpful coming out from spectral data, from hyperspectral data, is the type of material. Is this a PP or a PE bottle? And even if you can train a deep learning network or whatever, it will not be able to have the same color and shape and to be able to distinguish the materials. So therefore, this is the very big benefit of spectral data, of hyperspectral data. And yeah, different chemical compounds in the polymers lead to distinct spectra in the near infrared. They can look like the spectra shown in the middle, but of course, we don't only have 3 different types of material. We have like 15, 30 different amounts of additives that are used, or now we also have polymers, biopolymers. And there the differences might not be that super strong that I would say like multispectral is enough. So at least from my point of view, it helps quite to a certain point, but the power of the full spectral information and to make math on it and so on shouldn't be underestimated. So what we do is we have the camera. For plastic waste, it's the FX17 typically used in the shortwave infrared up to 1700 nanometers. Already quite a few years ago, the SPECIM Cube has been introduced together with a software called Insight. This whole concept, the camera, cube, software, everything you need to get the identification in real time of the material is called the SPECIM 1 concept. And it doesn't only work for the FX17, it also works for the FX10. It will work relatively soon for FX50 data too. So this in the middle is the data cruncher. And at the end, you have a sorting machine with valves, with a robot picker, with whatsoever to pick out the material that is not wanted. So that's the basic concept. And this is our way, how we think we can make it easier for users to say they don't want to get into the data processing, PLS algorithms, whatever. They want a result and they want it quick. So this is a solution for that. And it also works for black plastics. So that's what the FX50 is for. This is a hyperspectral camera made for industrial use in the midwave infrared, ranging from 2.7 to 5.3 micrometers. So the range that's typically covers quite well what is needed. And black plastics, so the carbon black plastics can be separated to PS, PE, PP, ABS, PVC. Of course, materials might be so dirty or whatsoever that it's not really possible. And there have also been some black plastics, especially for food products, that were only visibly black and not carbon black, not in the shortwave infrared. Of course, these black plastics can be sorted with systems up to 1.7 micrometer, but most of the plastics, our computers, our cars, whatsoever, are still carbon black, and therefore this FX50 helps to sort them too. Also, an example that was already mentioned is textile recycling. So it's incredible how many textiles, I haven't figured out the numbers, but it's an incredibly amount of waste, especially waste textiles that have never been worn, that are not used, that are brand new. That can be also one of the differences to plastic waste products, because this can be very dirty. Textiles are typically, as long as they are not full of oil or whatsoever, so that they are typically not super dirty, and you can also sort them out, the super dirty ones. And the sphere shortwave infrared spectral information helps to sort. So another example mentioned is construction waste, gypsum versus stone, wood, all these things that are used there can be used. Typically, it's a combination of different sensor data. It could be metal sensors. RGB cameras are quite cheap and used since long time. So this is the traditional normal way to do it. 3D helps in this type of applications to know how to grab the products. And yeah, it's just another application area. I will not go into the details for this foil. It's just a short part of a white paper that we've made that I will present on the next slide. The dumbest thing we can do is to throw our waste directly into nature. It has been done for a long time. We know it's not good. The next step is we have to collect it. That's done depending on the country, more or less. And then dumping it into landfill is the same idea as directly dumping to nature is not good. We need to sort and reuse our products. Also, energetic reuse might be a way to recycle, but it can be discussed if this is a real recycling, if you just burn it. So as mentioned, we had made a white paper already a while ago that is showing the situation, where can we help with hyperspectral imaging to get better sorting results. That it's a useful technology is, I think this is haven't be discussed anymore, and we are on a good way. So we are recycling more, we're doing more composting and so on, as these numbers show, but we are also nevertheless produce more waste, nevertheless. So that's it. And I added this one as the last slide. What can we do for each other? So what SPECIM can do for you is we can be your technology partner in hyperspectral imaging. We do this since quite a while, so we have seen a lot of applications. We can discuss about your specific applications If it's not 100% clear, of course, we can do some feasibility studies. And we can provide the out-of-the-box classification solution, SPECIM 1, which is reducing your time to market quite significantly. The other thing, what can you do for SPECIM? On a general base, be open for spectroscopy, for hyperspectral imaging. It's a known technology. It's known that it helps. So if you know somebody who's for whom it's new, just let him know about it. Contact us about your applications and needs if you have questions. Of course, you can use our cameras to do sorting machinery, sorting solutions, to build the recycling machines, or the analyzers that have also been shown. Please do a lot of research in new recycling areas too, like said, for pharmaceutics, for food, for example. And I think one of the most important things is find ways to make new products out of recycled material to really close the cycle, for example, for black plastics, but also for other plastic waste that will not find the way from bottle to bottle, but that is still there and needs some way to be recycled and not to be burned or dumped. And same topic for me, produce a good sphere LED lighting solution. To avoid especially the power consuming halogen lights. So they burn a lot of power. And of course, the lifetime is not that long. One important thing here is it should be affordable in a certain point of view. And just to mention, there are already companies out there doing it. One example is also here in the Munich area, the company MTD. They are combining, I think, 12 or 14 different sphere LED wavelengths. But yeah, nevertheless, it's still relatively expensive. It's rare to find. It's just started. And what I would like to have is phosphors that are broadband emitting so that the single wavelengths are not drifting to each other. That's from my side. Thanks a lot for your attention. And any questions, just let me know.
Thanks a lot, Gerhard. Super nice. It was, if I understand correctly, you already give some solutions that we were speaking at the very beginning, no? The challenge that we had from PICVISA and Sesotec on LED lighting and on black plastic.
At least for black plastics, we have something, yeah.
Yeah. What's the okay, Tobias seems to be doubtful. Please, Tobias, you can comment, huh?
Yeah, I've never seen a real feasibility on an industrial scale with the purities we really need and our customers need. So I'm skeptical about that.
Would you be open to do one?
For sure.
Okay, so let's get in contact, stay in contact, because we don't have a recycling plant, but we have the cameras. And if there's no study at all, so because black plastics are such a big topic, I thought there is surely something outside. And on the other hand, there's already companies using the FX50 cameras for black polymer sorters. Then it's up to them about the purity, the cleanness, and so on. So we cannot guarantee, because if you throw too much waste on the conveyor belt, the result will not be good. And this is a dependency of the machine, not of the camera only.
But you need throughput that pays off to get a good return of investment.
I agree.
Okay, perfect. But thanks a lot. Just a question from me. What makes it different and you are able to have this black plastic sorting for your product? What's the difference there?
So a question to me, or?
It's a question to you. What's the difference? And you're able to have black plastics sorting, just to make it clear for everybody, is different wavelength.
Oh yes, of course. The problem is that typically black plastics are made with carbon to be black, and this is absorbing all the energy up to 2.5 microns. So the standard typical used sorting technology is not capable to see the material differences, but the absorption of this carbon black is not that strong anymore in the midwave infrared. And therefore you see, again, the differences in the absorbance spectra of plastics. We have some spectra, of course, we do lab tests, but we don't have a recycling plant to make a full study about this.
We have already somebody who is willing to help you for that, no? So
yeah, and probably there are already some studies in preparation. Who knows?
Let's see. We have another question that comes from I read Wolfgang again. Wolfgang, if you want, you can ask the question yourself. You can unmute.
Yes, my question was, what is the spectral resolution of your camera system? So, if you have a spectral.
Okay, the sound is not good, so maybe I will do the question myself. I will repeat it. What is the spectral solution of your HSI systems?
The solution of the resolution.
Resolution.
The resolution.
The resolution.
No.
As the spectral resolution in the mid-wave infrared, because the wavelength area is more broadband, and typically absorbance bands are not super sharp in this range. So the resolution in the mid-wave infrared is 35 nanometers. You have roughly 9 nanometers per pixel, and then it's a slight oversampling. So it's 150 bands that can be used with like 35 nanometers full width half maximum. Yeah.
Okay. Thank you. I hope, Wolfgang, you got your answer. And then I would like to go to the next question that comes from Ross Stanley for KMMs. Ross.
Hi. I'm going to come back to this SWIR LED question again, because it's one of the business we're in. It's clear that in SWIR the LEDs are becoming less and less efficient as we go on, but they're nice because they have a small form factor, much nicer than tungsten. But it is actually possible, and we're developing this product, which is got basically like an LED-sized tungsten light bulb, which has a very nice emission, which can be focused down very tightly, just as tightly as an LED. And so the solutions, you won't get the huge lifetime of IR LEDs, but there is a real possibility that tungsten in a different use can respond to these questions with regards to intensity and power consumption.
Yes, of course, it's a good option. So one problem with halogen, besides the power consumption, is and the heat you also apply on the products you're inspecting, is the ban. At least in Europe, halogen lights are already banned because of their power consumption. So this is one of the problems. I think there will be exceptions, nevertheless, but specialized tungsten halogen LEDs, not LEDs, lamps, bulbs, will be needed for quite a while. I'm very sure about this. At the end, it's also about price. So if it would be a super expensive solution, probably not. Also, SWIR LEDs are still like more super expensive compared to a standard halogen bulb. So I think we will still continue a while with tungsten. Yeah, as there are specialized, very small units or whatsoever, so they can be very helpful, for example, for transmission imaging or for small field of use or whatever. The problem I see with big areas, so also focusing down to a very narrow line, and if you're illuminating with an angle, it's not always helpful because typically the waste is 3D. If it's flakes only, they can be only a few millimeters in height. But if it's regular household waste, they can be like 100 millimeters in height. And therefore, then the illuminated line is not there where you're looking at least not with our line scan based cameras. Therefore, the not super strong focused old school halogen spots are still doing their work quite well. Nevertheless, to save power, it would be nice to have it in the future. And then my strong wish would be a broadband broadband emitting phosphor, to have a stable output like it has been done for the white LEDs. And also there, looking back like 20 years, there was a very, very long development time to increase the power of white LEDs. It needs some time, and I hope there's also a will to do this in the NIR. It's already happening in the shortwave infrared over 1,000 nanometers. It's just started, probably.
Okay, thank you.
You're welcome.
Perfect, thank you. And we are sure that Photonics will give again the answer sooner or later. If we don't have any other question, I saw before a hands raising from Wouter, imec. You still have a question, Wouter?
I just wanted to pick in on the requirements for the LEDs, because that's indeed one of the things that we have also been looking in. But one is indeed the heat production of halogen lamps, and then evacuating the heat is not straightforward. So I hope to contribute to the discussion.
Okay, perfect. Thanks again, Gerhard. I don't see any other question for you. Thanks again for this presentation. And let's go to the next speaker for today. Our next speaker will be Ian Reilly from Vortex Optical Coatings. Ian?
Hi, good afternoon.
Good afternoon. You
just
can
sharing
share
my screen.
Perfect. The floor is yours.
Yeah. Okay. Thank you very much, and good afternoon, everyone. This sort of next 5 minutes is going to be a whistle-stop tour of the plastic sorting problem from an optical filters perspective. So, one of the things that really is a well-known need is the need for low-cost sorting instruments, and within those, optical filters are going to be a key component. So I'm going to sort of present some setups of instruments that we've been involved in our work over the last few years, and it might give some ideas to people to sort the problem. So I think, as we all know here, I'm perhaps preaching to the converted, but photonics is the answer here, and in particular IR photonics. If you look at the visible there in that bottom photograph, very difficult to tell the difference, of course, but when you go to the infrared, and this isn't an exhaustive set of data, of course, you can see from those two graphs there in reflection and transmission that there are quite a few points of difference, shall we say, and of course on those points of difference represent the pegs where we're going to hang our instruments that are going to sort this problem out. So I did say I'd talk a little bit about instrumentation, and there's two I'd like to consider. The first one involves using an infrared linear variable filter. So just a quick recap of what one of those are. It's basically a narrowband filter, and it changes the narrowband position as you travel from one end to the other. So in this particular example here, the narrowband is at 1.3 microns at this end, and then it's at 2.5 microns at the other. And it changes continuously and steadily in between. So this is quite useful because it can be incorporated into instruments. And one such instrument, here's a schematic of it here. We've got the linear variable filter in red, and then that's coupled to a line array detector. And with those two units there, you can make a compact mini spectrometer. So you can scan across the whole range, and with the associated electronics and software, you can compare that against known performances of these plastic materials. And of course, you can use that as your means of differentiating between them. And it does work, and there are instruments out there that are based on this principle. But there is a little bit of a problem, and that is the cost of the line array detectors. They're very expensive, and I've been looking at this over the course of maybe 7 or 8 years, and the cost doesn't appear to be coming down very much. So as an alternative, an instrument based on a single point detector may be a better option. Single point detectors are much less expensive when compared to line arrays. So the type of thing I'm talking about is using a filter wheel and a series of filters. So some setup that looks a little bit like this. We've got our single point detector in there in purple, and our filter wheel there as well. The light source is shining light on the plastics, and the reflection then is passed through various filters in the filter wheel. And this is used in the food industry for measuring things like water content, fat content, levels of proteins. So it's a wheel, if you like, that's already been invented as well. Where the difference is for plastic sorting is the filters in the filter wheel are very much focused on those points of differentiation within the infrared spectrum. So what I'm talking about here is in this industry over the last 5 or 6 years, the ability to make really tightly specified filters and narrow filters. That ability has improved considerably in the last 5 or 6 years. So it may be a very good option. So moving on to the traditional EPIC questions, what can we do for you? You've probably picked up that we can make linear variable filters, narrowband filters, and very narrowband filters. And of course, what can you do for us? Well, one of the things that I've certainly noticed in all of this is the need for low-cost detectors, particularly after 1.7 microns. Low cost in other components as well would be useful, and we've already discussed a lot about infrared LEDs as well. And the last thing really I want to mention is that we need to collaborate as an industry to solve this problem. And that's because the expertise is distributed amongst 4 or 5 companies, not any one company. So collaboration and openness is going to be key to finding effective solutions here. So just to finish off with, that's my contact details. We're actually over in the Vision Show in Stuttgart, probably with a lot of other people here as well in October. But thank you very much for your attention, and I'm open for questions.
Thank you, Ian. Thanks a lot. Ian is open for questions, so we're waiting for any from the audience if there is. One question: you have already implemented those kind of filters into hyperspectral imaging solutions?
Yes, we do supply to some instrument manufacturers that are already dealing with this problem. So it does work, particularly the linear variable filters. But the problem with it is, and I alluded to, is the cost of the detectors. Unless you make them yourself, linear variable unless you make the line array detectors yourself, it's very difficult to get the cost down to a method or a point that's going to give the the mass uptake of these instruments.
Okay, I see. Thank you. So one question comes from Avantes. Gerhard, the floor is yours.
Thank you, Ian, for the presentation.
I'm really sorry for interrupting you, Gerhard. Sorry, if you can hear me, we cannot hear you at all. So maybe you can try to remove your hands free.
Are you reading me now?
Yes, perfect.
Okay, then without the headset. Thank you for giving me the word, and thank you, Ian, for your presentation. One question popped up when you presented the filter wheel method. Don't you think that the scanning speed will be too low for the recycling industry if you're going for a solution like that? Because you have actually a scanning spectrometer.
Yeah, as I said in the presentation, I mean, the technique isn't really that new. It's used in the food industry, and I don't know if you've been in a food factory, but I've seen it being used when there's hundreds of chocolate bars whizzing past a second, and so they are able to tailor the electronics and the software to be able to cope with the amount of data that is produced. And that's really why I was saying that the success of this is going to be involving software, electronics, optics, as well as spectrometry.
Okay.
Okay.
Okay. Thanks a lot. Thanks a lot, Gerhard, for the question. So your feeling, Ian, is that this one can be in the future a solution to lower down the cost? Because as far as I understood, for the moment, we're just speaking about a potential solution, but still the cost keeps it away from applications. Is that correct, or I understood wrong?
Yeah, there's definitely an interest out there in doing this. As I was saying, the cost of line array detectors is a bit prohibitive at the moment, but you know, single point detectors with a filter wheel may be with the filters in the right place, may be a better low cost solution for this.
Okay. Okay. Thanks a lot, Ian.
Okay.
Thanks a lot for the nice presentation. Do you have any other question for Ian? If not, again, I would like to thank him and go to the next speaker. Thanks. The next speaker for today is Isaure de Kernier from First Light Imaging.
Yes, hello everyone. I will share my screen. Okay, is it working well?
No, we still cannot see. So you have to serve. I assume you haven't served yet.
Yes, yes.
Perfect.
No, it's working all right?
Yeah.
Okay, good.
And the floor is
Thanks
yours.
very much. So first, I'd like to thank EPIC for giving First Light this opportunity to talk about our technology and all its applications in plastic sorting. The field of plastic sorting is growing very fast, and I think this type of event is really great to bring together component suppliers, system integrators, and also final users. So in my presentation, I will focus on the optical sorting and the cameras that can be used for optical sorting. So a quick word about First Light Imaging. We're a French company settled in the south of France. Initially, we were created to transfer camera technology from astronomy labs to the industry. So the first cameras that we made were dedicated to adaptive optics applications. So for the last 10 years, First Light has designed and commercialized both visible and shortwave infrared cameras that combine very low noise to high speed. So by going beyond this usual compromise that there is between speed and noise, we have managed to provide cameras, high-end cameras, to both the scientific communities and also the industrial community. So our portfolio of camera includes two ranges. The first range, which is not too much of interest today, is the visible range that you can see on the upper left. But the one I want to focus on today is the shortwave infrared cameras. So the 5 cameras that are on the bottom of the screen. So here what you can see is that we have an entire range of SWIR cameras that go from OEM to uncooled cameras, tech stabilized camera, but also water and air cooling cameras to get the highest performances. And the camera on the bottom right is an extended range SWIR camera, which is able to detect wavelengths that are beyond the standard cutoff wavelength of InGaAs, which is 1.7 micron. So I will come back to this on the later slide. The advantage of InGaAs sensors in the SWIR region compared to other existing technologies such as MCT, for example, is that they do not need very deep cooling to perform with good performances. And also this technology is now quite mature and it's already used in spectroscopy, especially line array cameras. So to illustrate the importance of wavelengths for plastic sorting, I've included here a graph which shows the reflectance as a function of wavelength for some common types of plastics. So it's important to see that in the visible region, plastics here are reflective. You can see the color of the plastic, for example, on the water bottle at the bottom. But when you go to the SWIR regions, so roughly between 900 nanometers and 2.5 micrometers, you can see that most coated plastics have very distinct features. And also it's important to note that these distinct features, they go beyond the standard cutoff wavelength of InGaAs. So they go beyond the 1.7 micron. So for this reason, we developed two extended range SWIR cameras, which I want to focus on now, that are able to detect wavelength beyond 1.7. So we have one camera that goes up to 1.9 micron and one camera that goes up to 2.2 micron. So these cameras, they're really dedicated to detecting features that usually cannot be detected using standard InGaAs detectors. Shifting this wavelength of the material has some side effects on the cosmetic of the matrix. So this you can see on the right of the screen. And so at first light, we developed some embedded on-the-fly correction to be able to offer very high cosmetic images, even though the technology is very specific. So in short, what we need to remember here is that cameras with the right spectral capability can be used to differentiate and then later on, of course, to classify different types of plastics. So in my next two slides, I will show you two integration examples of first light imaging cameras into spectral imaging systems. So the first one is this system here. First use case is multispectral imaging. So this was a collaborative project with the University of Reims here in France. The camera was integrated with an 8-position filter wheel. So the idea is to run through 8 different filters to get different bands to see different spectral information of the image. So here the example that is illustrated is to detect the absorption band of water to see where there are moistures in the sample. And this can be used for moistures on plastics. So multispectral imaging is a very powerful research tool, but in this configuration, it's of course limited by the number of filters that you can use and also the time that it takes to move from one filter to the next filter. For industrial applications, such as waste sorting, there comes a need for very high throughput systems. And we've talked about this before. So in the waste sorting plants, you have to respect a certain speed to detect the different plastics. So we need to base these systems on very high frame rate and very high sensitive cameras. So here, hyperspectral imaging can combine spatial resolution to a very high resolution of the spectral information. So in this slide, what I show is a proof of concept that we made integrating one of our cameras, the CIRED 3 camera. So we integrated it in a push broom configuration for hyperspectral imaging. And here, when we make the camera run at full speed, we can acquire a hyperspectral data cube every second. So this is a very fast speed that can in turn enable to reach higher throughputs for plastic sorting. And of course, once plastic types are integrated in the software database, these can be discriminated at the speed at which we get the hyperspectral data cube. So to conclude, I want to come back on the two questions asked by EPIC. What can we do for you and what can others do for us? So as camera manufacturer, we can offer a full range of visible and shortwave infrared cameras along with the dedicated software solution. And by combining very high speed to low noise, we will enable manufacturers to produce faster solutions for plastic sorting and recycling. Also, because we really love to test things out and prove what can potentially be achieved with our cameras, we're always keen for fruitful collaborations and to test new applications. So if you're interested in that, please don't hesitate to reach out. On the other side, as end users or as system integrators for our cameras, you can provide us with important feedback on our technology, but also on the technology that you would need for your product. And this could help us then define the optimal cameras for sorting and design this camera to put it on the market. So thanks a lot for your attention, and I'm open for any questions.
Hello, everyone. This is actually Ivan from EPIC speaking. Let me replace Panos for a second. So, yeah, please go ahead, ask your questions and raise your hand. I will start with the question myself, Isaure. Do these cameras require cooling or temperature stabilization?
So actually on the full range, we have some cameras that can work without any cooling. And then we go up to air and water cooling. So this basically enables to bring down the dark current induced noise and enables you to reach longer exposure times. But I would say that for sorting, we're really interested in things going fast. So this is what we would consider short exposure time. And then the cooling is definitely not required.
Okay. And then if you have this water cooling, for example, or air cooling, does it make camera fragile? Because I can imagine in the waste sorting facility, there is a lot of vibration that might impact those fragile cameras.
So vibration is probably not the biggest issue here. I would say maybe the air, when you have a fan in the camera, you have some holes to let the air go out of the camera. And then this would be somewhat sensitive to possibly dust coming inside the camera. This would be the main issue. But vibration, except there's a very high level of vibration on the sorting machines. I mean, they are currently using other types of cameras. So I'm guessing it's not vibrating too much, but maybe I'm wrong.
Yeah, I believe there is quite some vibration, but well, as long as you don't, as the clients are happy, it works.
Thanks a lot.
And
Thanks a lot. Sorry, Ivan, sorry for interrupting. Thanks a lot for saving the situation. As you maybe understand, I for a moment had a technical issue and Ivan helped me solve it. So do you have any other question for Isaure? If you have no other question, I just want to
maybe I can ask. I'm interested in one more thing. Do you think Isaure is possible to push further the spectra beyond what was it, 2.2 micron?
So with InGas, technically it's possible. It's been shown, I think, up to 2.5 micron. But the main limitation is what I was starting to show here on one of my slides, is the defects that you get on your matrix. So the idea is that you get some crystal mismatch in the InGas. And I mean, at some point you have too much defect and you cannot use the detector anymore for imaging purposes, especially for hyperspectral, where they're very sensitive of the signal they get on one column of the camera to get the spectral data.
Okay, but if let's say we find a partner for you at EPIC that can push the spectra further with a different type of sensor, would it be actually interesting for the plastic sorting and waste sorting applications?
So maybe I'm not the best person to answer the question from the plastic sorting side, but I mean, we if there is an end application, we would be interested definitely in knowing about this solution. Now maybe someone else can answer the part about whether it's interesting to go beyond the 2.5. I think maybe there's something interesting in the black plastics that was mentioned earlier. Maybe they don't need to go up to the middle wave infrared, and they could work maybe from 2.5 to 3 micron or something.
Mm-hmm. Okay, thank you.
Thanks, Ivan. Thanks a lot, sir. We have one more question that comes from Marcela Gallardo. Marcela?
Yes. Do you hear me?
We can hear you, yes. We cannot see you. If we open the camera, it will be even better, but we can hear you.
Maybe this. Oh, yeah. Hi.
Yes, hello.
Hi. Very interesting. When I hear about the microns through which, let's say, the radiation has to go, I wonder about where the industry of packaging is going, because in reality, a lot of packaging is coated with so-called haptics coatings, and they are usually all kind of micropolymers that actually are those to provide a specific touch and haptic. So how can you identify, let's say, the material, the plastic, when you have at least 5, 6, 7, 10 microns of this material on top?
It's a good question. Maybe I think in some wavelengths you can see through some materials and maybe detect the materials that are beneath. But I'm not sure how doable this is in the case you're talking about. Definitely, I mean, what you're most sensitive to is the upper coating.
There are a lot of more and more packaging also when now you go buying food or anything. It's all about haptic. You have a specific haptic, and then you really use these coatings. I worked for 8 years in this industry, and I know that you cannot do without. So this is actually the real business making in a packaging world. And a lot of silicons are also used to also, they are in the picture, when it comes about haptics or about providing specific performances. So I wonder what I heard today is all beautiful, but I really wonder, let's say, what really is that can be done, because I work on the other side on characterizing these surfaces. And if it would be so easy to characterize the way that you said today, it would be fantastic. Let's say also on the other side where you have to develop the packaging. So I think there are a lot of challenges, and I was curious whether or not you take these challenges into account.
So, I mean, sure. What we need, and I would say, to take these challenges into account is to translate them from sort of the level that you said to real specifications for our cameras. So maybe that's the missing part to be able to move further with this.
Yeah. So maybe some of the packaging, when you have a bottle of polyethylene, but these bottles, okay, that is something, and a lot of science has been done on this. But if I look at the majority of the packaging of today, with these beautiful coatings, and whether they are sustainable is a different discussion, but they are very applicable to the market. To the point that there is so much going on now that they are going into renewables, bio-based or whatever. So, but they are there to stay. But we talk of several microns on top of the plastic or packaging that is there to provide the beauty, the performance. And you will have to go through these layers to be able to actually perform to the analysis then of the main body of the foil or of the plastic foils, for example.
Yeah, I understand the issue. Maybe I don't know if someone maybe from a hyperspectral company has anything to add on this. At first light, we really made the camera core, so I would say that this issue is one level too high for us to answer, but maybe someone integrating cameras and making the detection system could have a better answer to that question.
Okay,
thank
you.
I can tell you something about that, because right now we did not have any requests from our customers because of some coating. I think it also depends how it's applied to the packaging. Perhaps it can be washed off of the packaging with the several temperature solvent.
No.
Or it's not temperature stable and is during the reprocessing of the granules, it's getting off the material. That's also one of the possibilities.
Mm-hmm.
And if we're talking about the hyperspectral imaging, for sure, I think we cannot distinguish this certain material of the coating.
Mm-hmm.
But what I can imagine that the signal of the other polymer below it would be weaker, and that therefore it can be distinguished.
Yeah.
So if you have, for example, a PET coating with a really clear PET signal spectral image, then the PET signal will get weaker or has some disturbances, and then therefore perhaps with an artificial intelligence solution you can sort it out. That should be possible.
Perfect. Thanks a lot, Tobias.
Thank you. Thank you, my friend.
Thanks a lot, Marcella. And we have one more comment that comes from Richard Crocombe. Richard?
Yeah, hi. So just a quick note from the USA. So carpet fiber recycling is quite a big business there, and that hasn't really been mentioned in the talk so far. So if you're renovating a commercial building, you get a lot of carpet in, which is all basically the same material. So really for the past 20 years or so, people have used handheld near-infrared devices to identify the carpet fibers for recycling. This started off with a product that I think came from Belgium called the Carp ID. And in the mid-2000s, there were competing products from Axon Technologies and Polychromics, and all of these operate in the near-infrared. One item that's particularly of interest is you do need to distinguish between nylon 6 and nylon 6,6, because one of them can actually be depolymerized and turned back into a feedstock. That turns out to be fairly tricky, and you need fairly long wavelengths in the near-infrared to be able to do that. But it's perfectly possible using a handheld near-infrared device. So I just thought I'd mention that it might be worth thinking about carpet fiber recycling as well as the sort of standard plastic waste recycling. Thank you.
Thanks a lot, Richard. Thank you. Do you have any other question or comments following the presentation of Isaure or the comments of Richard? Seems that not. So with this one, I would just like to share my screen. So what we spoke about today, we spoke about plastic sorting, waste management, and what is essential for the circular economy. It's hardware and software combination. Combination of different technologies. We need different spectroscopic techniques or photonic applications in order to have a fully functional plastic sorter, including black plastics. Use of a wide spectrum or use of new sensors, efficient lighting devices in the infrared. Also, we will have some demands regarding that from our end users. The needs of the market is faster acquisition, easy to use and adaptable devices, and more efficient software and hardware combination, which I'm sorry, I just repeated. And what are the challenges? The challenges are detection of black polymers. Some of the people today, they spoke about the possibility to have those black polymers sorting devices, and also LEDs that can emit powerful enough for between 1,300 and 1,900 nanometers for near-infrared detection. So with this one, I would like to thank all our speakers for the very interesting talks today, but also all the participants for actively participating in those meetings. And please remember that if you want to get connected with any one of the speakers or of the participants, you can come back to me with an email and we will do that. Thanks again and have a nice evening.